Direction fields. So if we think about a first order differential equation, like our example here, y prime equals 2x plus y. If we think about a first order differential equation, we've got y prime equals a function of x and y. So what you really have then is a slope formula. So if I ask for what's the tangent slope to the curve, okay, what curve? The solution to this differential equation is the curve of which I'm speaking. But if I want to know the tangent slope, that's what the differential equation is. It's the tangent slope formula. So what's the tangent slope at the point 0, minus 1, when x is equal to 0 and y is equal to minus 1? The slope's minus 1. How did I get it? I just made x equal to 0 and y equal to minus 1 in the formula. What about some other points? Well, any xy point that I give you, 3, 2, let's say, if I talk about the point 3, 2, totally just pulled that out of the air. If I plug that into the slope formula, what do I get? 6, 8. I get the slope as 8. So at the point 3, 2, I'm down here in the graph, that's supposed to be a slope of 8. That line is a slope of 8. Yeah, that's what a directional field is then. Here's an example of a directional field for this equation. What am I doing? At each point, I'm plugging into the slope formula, to the differential equation, getting a value out, so 0, minus 1, 0, minus 1, this point here. And I'm drawing a slope, a little tangent slope, at minus 1. I guess for you looking, it's like this. But anyway, at each one of these points, you draw a slope, and that gives you the slope field or the direction field. So the solution then, these lines are supposed to be tangent to a solution. So if I give you a starting point, let's say here, and I'm drawing the curve, drawing the solution, it's supposed to be following these arrows. These arrows should be, these lines should be tangent to it, so you can get a solution curve to it. Now, I would never ask you to manually draw a direction field. It's tedious to draw all these little lines, but we know we could do it. It's the kind of thing that you would ask a machine to do, like I did here. So although you wouldn't be asked to draw one of these yourself, you should be able to recognize, like match what a direction field looks like for a particular equation, or what an equation, what a differential equation would sort of come out of what direction field, matching one to the other in kind of a multiple choice kind of way. We do, though, if you were going to be asked to draw this, one of the things you could do is, let's find all the places where the slope is equal to 0. All the places where the slope is equal to 0. Well, we can go back up to our differential equation and just set y prime equal to 0. If I set the y prime equal to 0, then I get these equations of 0 equals 2x plus y. Or I guess another way of writing that is y is equal to minus 2x. So that's the curve where, that's along here, everywhere on this curve the tangent slope is equal to 0. That's a nullcline. Cline for slope, null for 0. It's the curve in the direction field that connects all the places where the slope is equal to 0. Now 0 is a version of it, or makes a nullcline, but we could have picked any other number. If I set y prime equal to some other number, like let's just say I set y prime, I'm picking this arbitrarily, y prime equal to 2, that's going to give me the curve I'm looking that connects all the places where the slope is equal to 2, or 2 is equal to 2x plus y, or I guess I would write that as y is equal to minus 2x plus 2. That's the curve, all points on this curve, minus 2x plus 2, so it goes through here like this. That would be then connecting these 2 points here. That's the isocline, iso for the same, cline for slope. It's the curve that connects all the places in the direction field that have the same slope together. 2, I could have arbitrarily chosen this to be 5 or whatever. A new example. Y prime is equal to x minus y squared. And I guess we can, right away before we draw the direction field or have the machine draw the direction field to that. So before we draw the directional field or have the machine draw the directional field, we can talk about nullclines. If I want to make the nullcline, I'm going to set the slope equal to 0. So I end up getting this, I guess, this sideways parabola of x is equal to y squared. So this sideways opening parabola that goes through the origin is going to connect all the places where the slope is equal to 0, the nullcline. If I want an isocline, then we're setting all the places where the slope is equal to, let's just make that k as a set number. I'm setting y prime equal to k, and I end up getting these parabolas, sideways parabolas, that connect all of the places where the slope is equal to k. Those are the isoclines. Let's see what this looks like. Now, to draw this, I drew this in Maple. There's all sorts of other symbolic manipulator programs. I think if you have one of those TI-89 calculators or whatever, the picture on the box has one of these, so I assume that they can draw it. I would just go to a website. Here's one now. I think I just Googled slope field plotter or directional field. There's a bunch of these. And I typed in the equation, and it drew for me the directional field. I can kind of see this sideways parabola here that's the nullcline. And there's the slope field for it. This lets me adjust things, which is kind of fun, but they all do that. Now, I'm going to pick a starting point and then have it draw the solution. So we pick the starting point, and then it draws the curve such that the curve it draws is tangent to these lines going forwards and backwards. So that would be a solution curve that goes through. Drawing the curve, we could do that with Euler's method, right? Essentially, is finding these points along here. There are more sophisticated numerical systems than that, but it's like Euler's method. Let's put in another one. Starting at this point, following the tangent. Put in a couple more. This here, so this curve, if I run backwards in x, they look like they become the same curve. They totally cannot be the same curve because of existence and uniqueness. They have to be very close to each other from the picture, but there's space in between those two curves. One of them, because they split here, how do I know they don't join? Well, let's say they join somewhere like here. If they do join at this point, then what's the slope at this point? If it joins at this point, the tangent slope has to have two values, one to go off on this direction and the other to go off in the other direction. My y prime is defined. It's this x minus y squared. It's a defined continuous formula. So existence and uniqueness theorem says that there isn't going to be a point. There isn't going to be an xy that I can plug in here that will give me two slope formulas, so it can't split up. So these must be unique curves traveling around here. There's a direction field. Type in another one. Let's just, for funsies, what if I made this cubed? Now the y equals x cubed is the nullcline, and I get different solutions. Everything's going off to a flat number. If we solve this, it's nonlinear, so that wouldn't be easy. But if we did solve it, then the limit as x goes to infinity, all of the, regardless of the starting conditions, should approach some flat number. Anyway, directional fields.